Thank you very much. We appreciate your effort to introduce our names. But I will do it again, okay? So we are Błażej Kubiak and Krzysztof Kudrynski. And in this talk entitled Deep Learning in Computer Vision, we will be talking about deep learning in computer vision. Surprise, surprise. The plan for this talk is first to get extremely excited. And we are dedicating 7 minutes especially for that. Within the next 22 minutes, we will truly understand the concept of convolutional neural network by a quick Python coding session. And for the rest of the talk, we will go through our own challenging real-life project where we will hopefully see amazing possibilities of modern AI. So amazing that you might even get scared, for which we especially dedicate the last minute of our presentation. So, let's talk about science fiction, a classic from 1982. In this scene, Harrison Ford is analyzing a photo using a super mega computer. It is year 2019, so we can obviously zoom and enhance beyond any physical reason, but that's not the end. This computer can even look around corners. What a technology. This film is a classic. It's really great to watch, but although the film was shot when I was still very young, even then I could feel something is not right. And I'm sure that everyone here who watched this scene felt this little bit of embarrassment while watching that. If you did, well, 2019 is not yet over, and the world of science already says that we are actually able to reconstruct details that seemingly could not have been captured by the camera due to its physical limitations. But okay, we can believe in zoom and enhance, but seeing around the corner, well, come on. The end of 2017, guys from MIT published a method in which using a camera, you can trace objects around corners. It's actually done by looking at the direct reflections, and you can trace these objects with centimeter level accuracy. Now, isn't it amazing? Maybe it does not see the face of the android lady behind the corner, but 2019 is not yet over. And this technology was developed by people from blood and bones, just like us. Next scene, Eagle Eye, a film from 2008, where a super intelligent computer is trying to take control over the world, and people try to hide from it in a soundproof room, switch off all the devices, and hide in the shade, but the machine reads their conversation from the vibrations of water. Impossible? 2016. Guys from Microsoft, Adobe, and MIT published technology which does even better than that. We are now watching a video of a flower listening to music. So the flower is in the place where the music was played. And it's a video. And now it's the same video, but the music was reconstructed from the micro vibrations of pixels in this video. And these micro vibrations were of degree of 100th of a pixel. Amazing? Well, this technology was developed by people from blood and bones, just like us. Finally, awaited by everyone in this room, David Hasselhoff and his talking car. The car talks. Well, that's not too extraordinary. It knows what it is talking about. And it can describe its environment even better than Uncle Bob can name his variables. 2015, a machine is able to semantically segment an image and generate grammatically correct sentence about it. All these image descriptions were generated by the machine. Is it impressive? Well, if this is impressive, then you are not ready for the next slide. Also 2015, guns learned to draw photorealistic images based on what you say to it. No one has ever made this photo. This bird does not even exist. Similarly to any of these. This is how a machine learned to imagine a sentence. And this technology was developed by people from blood and bones, just like us. But let's not forget that our car can actually drive itself. Impossible if there is anyone here in the room who thinks that self-driving cars are still science fiction. Well, congratulations. But please wake up and, I don't know, buy internet. A lot is going on in this field as we speak, and these technologies are being developed by people from blood and bones. This time, not like us. I could tell you exactly who wrote the patents, but ladies and gentlemen, we are very shy. So the cars drive by themselves, robots do their job on their own, they learn to see, they learn to fly. We live in these amazing times where all of these technologies are at our hand and we can participate in their development. And I'm sure you are getting thrills to start this amazing adventure today by classifying cats and dogs. We won't do that, that's a joke. But to get the fundamentals, we will start with something relatively easy, which is classifying faces into glass carriers and normal people. Do we need AI for that? Well, let's first try to think about it in a traditional, step-by-step computer vision way. So we have a sample lady from some data set, and to detect her glasses, let's first find some edges in this photo. To do that, we apply horizontal and vertical filters to the image. Speaking mathematically, edge filters will be just small matrices which correlate with the change in color intensity. So going from 1 to 0 to -1 would detect, for example, a left edge. And now we will be filtering, which means we will be doing convolution or correlation operation, which is simply sliding such a filter across the image, multiplying the pixels of the filter with the image and getting the result. And in this way, we get the result, like this. Is there anything in the world easier than that? No, there isn't. But however trivial and however obvious, convolution is the most important operation of our today's talk. Now, let's zoom out our image to look at it at a further perspective. But we'll not do it by typical resizing, because with typical interpolation, while resizing, we will lose the edges which we just detected. They will be blurred off. So instead, what you can see, they are still sharp and very shiny, which means we are taking maximum value while we are resizing, which you can see in the diagram below. This is called max pooling. And is there anything in the world easier than that? No, there isn't. But, however trivial and however obvious, max pooling is the most important operation of our today's talk. Now at that scale, we can try to detect our frames, and the frame we can detect using the edges detected before will be just a rectangle enclosed by vertical edges and horizontal edges like this. When we perform convolution, we will see there are two frames here. We look at it at further perspective. Now we just detect two dots. It's a very simple filter to correlate the two dots with. And after that, we zoom out a little bit. If there is a dot somewhere in the middle, or if there is not, depending on that, we have some result. And with that, we can see that this lady, with 97%, she has glasses, which is a good result. Now in code, an image is a matrix, and many multi-channel images is a tensor. Here, n, because we have n images, by 200 by 180, which is the size of the image, by 3, because we have 3 channels like RGB. If we design a filter, it needs to be a 3-channel filter, because that's a 3-channel image that we are correlating with, and the result would be n images, all of them 1 channel, because as we said, convolution just multiplies everything even across the channels and sums up to 1 number. But we could design more filters, and then each result would fall into another channel in our output. Details are now not very important. What is important here that, in fact, here we are designing a graph of TensorFlow. And there is actually a library with that name, so we'll use it. We first create an empty graph, and then we'll use a session to feed the data placeholders with our images from the disk. And, in fact, from performance, even loading the data can be part of the graph. But now I see this question in your eyes, where is this whole artificial intelligence? Nowhere. But beware, it's coming. And in case you are planning to have a short sleep now, I'm telling you it will arrive suddenly. Okay, so let's start our implementation quickly. We need TensorFlow. We need NumPy, we need OpenCV and OS. We will build our graph, we will read the data, we will run the graph and show the results. In our graph, we put a placeholder for input data. There will be 200 but 180 images, 1 channel. We don't know how many, hence the none. We also create placeholder for labels, because we will load faces with and without glasses from different folders, so we know who is who. Labels will be 1 for glasses and 0 for no. We will soon prepare a class, let's call it filters, which will have separate methods to create and return a filter, which we need. 1 for edges, 1 for frames, 1 for glasses, and 1 for final classification. And now the graph will be very simple. We take our data from our placeholders, we filter it and zoom it out, as we discussed before. And first we will be detecting edges, and we'll zoom out by 10 times. Then we will detect frames and zoom out a little bit more. Then we'll detect glasses, zoom out a little bit, and finally we will classify. And in the end, we will have some results. So let's calculate some metrics, how well we did on more examples versus the labels. And we can do it automatically because we have just loaded the labels. So for every detection, we know if it was glasses or no. So we can compare our detections with the labels. And let's calculate accuracy and cost. Accuracy is simple. I think everybody understands. Accuracy is just the percentage of correct predictions, where the prediction can be just right or wrong. Cost is something more. It is defined as a continuous function. For example, detecting glasses for 97% for this lady seems correct. But a justified question is, where did the 3% go? And the 3% is a loss, a small one, but it's a loss. Now, in another example, for some reason, our detector was really confused, and while it was still correct, now there is much more uncertainty here, and the loss is much higher. And finally, when our detector sees Harry Potter, it says 99% sure he has glasses. And however sympathetic we could be about this decision, the loss is quite huge and should be like infinity here. We cannot be so sure that the guy has glasses if he has not. So now we have our metrics, accuracy and cost. We need to load the data. We create a class for that. We have photos in 2 folders. 0 are people with healthy, typical eyes, and 1 is the elite with glasses. Let's create a method which will load the data. We will work on several photos at once in batches. But as we mentioned before, we will perform the actual loading of images and labels as part of our graph. So we need to create a session for that. So let's create one, and finally we put, in place of the placeholders, we put our data. And when we do this, with the same data, we will first print some metrics and then display some results. Okay, and now we would need an hour or two to implement all that, which we just prototype. But most of these things, like displaying images, like reading files from the disk, and so on, are really trivial. And it would be too much time to waste at the moment. So instead, we'll do it very, very quickly now. You can obviously try to follow while it is being written. But it's not the aim that you understand every line being typed. It's just showing the full coding session to give you the impression that the whole experiment is within the reach of 1 or 2 hours of coding. And during this talk, we will focus on the most important part. So we have all the helper functions and placeholder for the methods defined. Let's focus on the problem. We need to implement filter and zoom out function. We will filter using convolution, which we have in TensorFlow. We will filter and shift our mask one by one and pad the results so it's the same size as the input. And now let's implement the mysterious filter. In fact, 4 filters, all 3 by 3. And what is a filter? I already told you, it's just a small matrix that will correlate with the features you are trying to detect. So in the left edge would be just the decreasing intensity of pixels, which you can see from 2 to 1 to 0, and so is our filter. The right filter is just the flip of the left filter, and the bottom and top edges are just transposed and flip transpose. Let's see the results. So we see our 2 sample faces, one with glasses and one normal. We have our 4 filters, and we have our 2 results, 4 channel for each result. Now if you look very carefully, you might notice that the first 2 channels, so left and right, are almost the same, very similar. The same is for the last 2 channels, because they are in fact symmetric. And this is because the left filter is just the negative of the right filter. The left was 2, 1, 0, the right is 0, 1, 2. So it's just, it's calculating the same thing, but negative. And we don't like this. We want every filter to do its unique job, to have a single responsibility. But we can easily fix that. What we can do is we can just cut the negative part. This is so easy. But before we do it, try to think how you would name an operation that would cut the negative part. Cut off negative, negative to 0. Respect to the guy who came up with the super intuitive name, rectifying linear unit. In short, ReLU. But that's not the end. The world of science went crazy. ReLU is believed to be the greatest breakthrough in the world of artificial intelligence. You can even see it penetrating into the world of pop culture and art. But is there anything in the world easier than that? No, there isn't. But, however trivial, however obvious, ReLU is the most important operation of our today's talk. So, it is also implemented in TensorFlow. Let's add it and show the results. Well, now we have our edges detected without the negative part. We are very happy. It's very beautiful. So now let's zoom out using max pooling. We will zoom out by zoom times with a zoom stride and traditional padding, and then we will show the results. But after, for the first time, after detecting edges, we set the zoom to 10 times. So you can see the results are much, much slower than the, smaller than the original one, which is very, very aggressive approach. But what you can see that if we were detecting the glasses in the original picture, the filters would have to be very good because each frame of the glass would be like 50 by 50 pixels, more or less. Now, after 10 times pooling, single frame is like 5 by 5. So we need a very small filter to detect that. 5 by 5 is enough. So we will do it. And it is the filter working on 4 channels now because we have a 4-channel input. And because in the first 2 channels we detected left and right vertical edges, and in the last 2 top and bottom horizontal edges, we can create our typical frame detector as a rectangle enclosed by vertical edges from the left and right and horizontal edges from top and bottom. Very easy, we run. And when we see the results are very beautiful, we see 2 frames detected as a pair of 2 bright pixels for the first lady and nothing for the second. So now, to detect the glasses is a no-brainer. We create a filter which will correlate with 2 dots. Let's get dirty with our implementation. 1 dot here, 1 dot here, done. And in the result, we will see a beautiful shining dot somewhere between the eyes of the young lady with the glasses, and nothing for the other traditional lady. And now, after a few lines of really trivial code, we can classify this. We arrive at the final result. We finish with just 2 pixels per image, corresponding to 2 classes. So top lady has glasses, so the right pixel, which says has glasses, is shining more white, while for the second lady, which doesn't have glasses, the bottom, the left pixel shines a bit more, which is a good result for us. Adding a few more guys, and we run, and first glasses found, second found, now third and fourth, we are reached by the brutal truth about life, which says that not all glasses look like windows. And so as you can see, for the more difficult cases, from the different perspective a little bit, a different kind of glasses, we were wrong. What to do? Let's sum up our status for the moment. We designed a network composed of layers of just 3 operations. Convolution, ReLU, and max pool. And for each convolution, we manually crafted filters, which you can see here. For each convolution, we did it manually. Every pixel, we set the values with our hands. And sometimes, sometimes our solution works. Sometimes, for the more difficult cases, it doesn't. Could we make it better? Sure, we could play with these filters, tweak and tune them to detect more difficult cases, check them, add more cases, tune them, and in this way, improve the accuracy and cost while we see more examples. We could do that, but we will not. Instead, we will set our filters with random values. What will it detect? Nothing. But then, looking at more and more examples, we will let the machine optimize the weights of the filter for us, and we will do it by adding 1 line of code. So, ladies and gentlemen, it is arriving. They tried to capture this moment in the Terminator. They tried in the Matrix. But it is actually you, ladies and gentlemen, staring at this line of code being typed in. It is you witnessing the death of handcrafted human solution and the birth of artificial intelligence. minimization of the cost function. Artificial intelligence is basically just minimization of the cost function. Just good old math, but put into powerful computers. Now, is it disappointing? If you expect this supernatural phenomena and the touch of human wand, yes, the truth might hurt you. But on the other hand, if you realize what we can achieve with such theoretical simplicity, it blows your mind. In our case, while writing this code, even our operating system got intimidated by the emerging artificial intelligence, and it also asked for an update. Coincidence? I don't think so. But anyway, after a few technicalities, your convolutional network starting from some random values in the filters will step by step be able to learn more optimal filters to do your job. By seeing more and more labeled images, it will shape itself on its own. And you can see that similarly to us people in the first filters, it tries to detect some edges. You can see that there is a left edge, top edge a bit skewed, and so on. So it tries to detect something like this. In the later stages, it finds something much more optimal than we did. But it did it. And here we arrive at the accuracy of about 80%, as you can see, which is quite okay. If you were to do it manually, that would be a lot of work. And but 80% is not so much. But it's a very small network. It's a very small network. And now we don't need to craft all of the pixels of these filters by hand. We don't need to do it. So we can just make it bigger because the machine will do it for us. So now you can observe how our machine crystallizes the solution which is beyond any handcrafted design, reaching the accuracy of 100% on a validation set. So, is deep learning just stacking more layers as the complexity of the problem arises? Not exactly. Because every layer comes with responsibility and risk. Deep learning, deep networks are very hard to train because they are trained by backpropagation. And so the gradient, which is propagated back through the layers, can become unstable. It can vanish or it can explode. And as this field of science evolves, new ways to solve these problems rise from traditional techniques like smart initialization of weights, regularization, gradient clipping, and design of new activation functions, up to solutions that are so clever that you have thrills when you read a scientific paper, like introducing interlayer auxiliary networks to speed up training of the first layers of the deep network, or residual connections to put every detection in the context of the previous layer. We could talk hours about various beautiful solutions emerging in this field every day. Probably even at this moment, someone is writing a paper which will revolutionize the world and change the state of the art. But what seems to never change is the fact that in order to train such huge networks, we need huge amount of training data. Sometimes hundreds of examples, sometimes thousands, sometimes millions. And is that respected with the newest science fiction from 2018? The Expanse, distant future, a group of main characters is looking for a missing girl, searching through old video logs, having only one photo, a single photo of the girl. Will the algorithm be able to find a girl having a single training example? Of course it will. Impossible? 2019, the 1st of May, CERN. Vox Days Conference, a project by Krzysztof Kudrynski and Błażej Kubiak, reveals how to make that happen with a few mathematical tricks.
Yes, thank you, Chris. Chris gave us a very deep introduction to our practical project. So let's continue this case where we are trying to find someone in in the video. For example, the girl. So for that case, we could train network to classify girl and other people. But for sure, you can imagine that the data set would be really imbalanced. So we have only one positive example, and like 1,000 or millions of other people faces. So it will be just impossible to train such a network. But on the other hand, if we find someone else, for example, Chuck Norris, it would be a completely different thing. Why? Because in the internet we can find more pictures of Chuck Norris than all other people pictures, in fact. So, but is it okay? And we found. And these are just samples, but believe me, there's 1,000 of pictures of this guy. But would it be a really good solution to train such network? It would work only for Chuck Norris, not for me, not for Chris, not for anyone else. And our aim is not to actually classify Chuck Norris, but to say for two randomly selected pictures of faces, to say if these are the same faces or belongs to different person. And actually there is specialized class of neural networks that can solve that problem. The difference is that at the end of the network we have, instead of the output, like a class output, like the Chuck Norris or the girl or other person, we have a feature vector. And we call it sometimes face embedding, and we can think about it like kind of face description of face signature. And we train this network in a tricky way. So if we feed the network with two faces, we have those feature vectors, those signatures, and we try to train them to maximize distance between those signatures if they belong to different persons, and minimize distance if these are the same faces. That's why we are not using traditional loss function that compares expected output value of the network and actual value that is currently gathered from the end of the network. But we use the loss function that comes from this assumption that I said before. So minimize distance between B and C and maximize A and B. And however nice solution it is, and it is widely used when you go to the Google web search and find someone by picture, it will use this kind of solution. And there are nice papers about that, and I encourage you to read those. We'll try to do something simpler today, something that will be really small network that we'll be able to train today in 5 minutes. And let's see how it will work. So what we know about the previous network is that it is quite tricky to train this kind of network, but we also know that it's quite simple to train the network for classifying celebrities like Chuck Norris, Steven Seagal, or other legends. So if it is so simple to train such network, what we will do now? We'll download ready network from the network. And we will make small surgery. So we will remove this classification part at all. And what we have at the end of the network now is a feature vector. And it comes from the network that was trained for face recognition. So for sure it contains some nice properties, nice features of faces. But of course, it wasn't trained to maximize this distance between these vectors. That's why we want to use simple equivalent distance. But we will feed the network, gather our feature vectors, subtract them, and we train very small neural network, just 3 layers, to say yes or no. So it will say yes if 2 pictures are the same faces, and no if very different. Okay, so how we can do that? Of course, we need data set, so we will grab it from the network. This is a big data set of celebrities, thousands of them. And we will feed this ready network with randomly selected pairs of pictures, and we will say yes to our network if these are the same faces, and 0 if they are different faces. Okay, so let's try to train our network. We will use for that Keras because it is actually the simplest library that can be used for deep learning. If you want to start with machine learning, it is way to go to start with Keras. It is in fact wrapper over TensorFlow and other frameworks, but the API is really nice and really easy to use. And to define the network, we just define the 3 layers. We define optimizer that will be used. Adam is mostly used optimizer these days. We compile our model, and we can just run our training. So let's go to the demo and try to train our network, and we'll see if demo will work today. What is nice about Keras, it also comes with nice visualization of the training process. It's just out of the box. You see what is going on. Every batch you see what is average accuracy on the training data set, and every epoch you sometimes see when epoch is ending. You see the accuracy on validation data set. I run it for 10 epochs, and maybe accuracy is not so big. We don't have time for longer training, but let's see how it works. Krzysztof, can you help me? So we'll need some volunteer. We'll take the picture, and we will see if other guys looks different or maybe similar to the person.
And a volunteer that wants to be detected? Oh my God, there's 2. So what do I do now? I will start with you, and I will try to detect you later. Can I have more light? Is it okay to have more light for the audience? Okay.
So we are running a demo. It will try to, yeah, it is. But maybe.
Okay.
What will be better if you? Okay.
What's that?
It's okay. Okay, so now we see faces that are detected or something. Something is wrong.
Sorry, I will come closer maybe. It's very shaky. I don't know how to grab it. Come on. I don't know what's wrong. Maybe the light? So look at the camera. Can you look at the camera? What the fuck? Let's see. What's up?
Okay, let's run again.
Don't panic. Demos always work. But it's not good. It's not good. Something is broken.
Maybe.
Can I show? Can you try for myself?
Yeah.
Did it do or no? Who is that? It's artificial intelligence. So let's restart. What have you done? You don't know. Okay.
Maybe try with another person.
No. We'll check again.
Does this mean, you can't make a Terminator with my face.
No. The problem is with the first network, which does not detect faces at all, which is the SSD, I guess. Oh my God. I'll check with a better light, maybe somewhere. Sorry, guys. Where is the best light? Uncle Bob? No? But no faces.
Oh, shit.
As me, like, I have like a good face.
Co się stało?
Can we lower the light? Because I think with lower light it was better. Try it now.
Can I have you? Is it working?
It is wrong.
Can you come here for a second? It's.
But orange guy is always
Can you
detected.
stay somewhere here, like we? Maybe it's the case of light. Okay. Okay. Now I don't know why it's better here. I don't think so. So.
Yes.
Oh, maybe.
Yes, there must be one.
Yeah.
Yes, we
Okay,
Yes,
but now
we
generally the idea is that
we forgot the if that we have, that there must be only one person to select one person for
Okay.
as a reference.
But what
phase.
happens now, whoever we show, is the red. And if I show the guy I'm looking for, stop, it's green.
Usually good.
Whatever face, can you smile? Or
Yes.
so,
And face to the audience.
yeah. Come on. No, now when we know our software, anyone can can try. Is it okay? Are you convinced, or do you want more, guys? Okay, thank you. Odpalić kreskę? So, artificial intelligence did the job. It was the human factor that failed, you know. Okay. Does anyone know what is that? Have you seen this? No? The top cross is what the person is looking at, and the cross below is what the machine generated by analyzing their brain activity. More examples here. To me, it's a bit disturbing. Maybe it's not a fully deserved reading in your mind, but that's clearly a first step already taken, already tested and documented in the literature. And soon the machine will be able to read your minds, maybe not very soon, but it is going to learn any task you give to it, and it will always do so by optimizing the objective function that you give to it. So whether you design it for saving your planet or for winning a board game, please make sure to double check two things. First is to set the cost of human life to infinity. And second, check if infinity is properly implemented in your environment. Thank you very much. Any question? Okay, you can tell something.
Thank you very much. Yeah, we have 1, 2, 3 minutes for questions. So if you have them, now is the time to ask. Yes, please, in the back.
Hello. Thank you for the talk. It was super entertaining. Question about the sample size. Let's say something like the glasses, non-glasses. How many pictures will you need, and how much time will you take to train, like on a laptop? Is like
we can check that, but it was only hundreds. It was like maybe 1,000.
For both categories, or like the two folders, like 1,000 and 1,000?
Well, I think for both of them, but it doesn't matter. It's such a small sample size in this case that it's a very simple task, by the way.
Okay.
The task for classifying people into celebrities and then to learn it to detect different and the same, it's much more complicated. But what we trained here was not to, we had the base network and we cut off the last part, which says that the most difficult part was trained before. And we only up-trained it to say it is different or the same, okay, to make it in this place.
Thank you.
No more? Thank you very much again.
Thank you.